Okay. So lots of problems in where is this thing? All right. So lots of problems in formal methods can be formulated as logical games. These are two-player games of perfect information in which the rules are written in some sort of logic. So for example, functional synthesis, the problem of finding a program to match some input-output specification, can be formulated as a universally quantified, or a for all exists formula of the form for all inputs there exists some outputs such that some spec holds. Reactive synthesis is the problem of synthesizing a program that runs forever, interacting with its environment. It can be posed as a formula with infinite quantifier alterations of the form for all events there exists some response, such that for all events there exists some response, and so on forever. So in this paper, we present algorithms for synthesizing winning strategies for two classes of games in the theory of linear arithmetic. The first is satisfiability games, which are games of finite duration, like functional synthesis. And the second is for games of potentially infinite duration, like reactive synthesis. There's a connection between these two different classes of games, and we'll get to that in a bit. I'll start out with satisfiability games. Now, the idea is that I can view a formula as being a game between two players. Sat wants to make the formula true, unsat wants to make the formula false. And the game is played by the two players taking turns instantiating these quantifiers. The existential quantifiers belong to the sat player, the universal quantifiers belong to the unsat player. So a play consists of a sequence of choices for the quantifiers. So for example, sat might start out by picking 1, then unsat picks 2/3 for x, sat picks -1 for y, and unsat picks 1 for z. So the sat player wins this play if, when we evaluate the matrix of this formula using the assignment that we've computed in our play, the result is true. And conversely, if the formula evaluates to false, then unsat wins. And it's not too hard to see that a formula is satisfiable if and only if the sat player has a winning strategy for this game. So this is some algorithm for picking instantiations for the existentially quantified variables such that no matter how the universally quantified variables are instantiated, the result is a model of the formula. So here's an example where I'm going to pose a specification of a least upper bound operator. The specification has two parts. The first part says that this least upper bound is an upper bound. It's greater than both x and y. The second part says that among all other upper bounds, the least upper bound is least. Right, so I can just convert this into pre-next normal form, and I have a satisfiability game. A SAT strategy, a winning SAT strategy, is a function that I can use to instantiate this least upper bound operator. So it's a function that depends on the two previous moves of the game, x and y, that I get to see, but not the upper bound operator that is hidden from me. the winning strategy is just any way of picking the least upper bound such that the formula is always true. It always corresponds to an implementation of the least upper bound operator. So the winning strategy is exactly just an implementation of this procedure. So how do we synthesize winning strategies? So a couple of years ago, we proposed an algorithm, a decision procedure for linear arithmetic that basically does this. And the idea is that we can synthesize a winning strategy for one of the two players by mutual strategy improvement. So we'll begin by posing some candidate strategy for SAT. Then we'll find a unsat strategy that beats the SAT strategy. Then we'll find a SAT strategy that beats that unsat strategy, and so on, until eventually we synthesize a SAT strategy that the unsat player can't beat, or vice versa. So something that might be worrying to you is that what makes this process terminate? And the answer is that at every round, not only do we require that we synthesize a strategy that beats the opposing player's strategy, but it also has to improve on our previous strategy. And what does it mean for one strategy to improve on another? A strategy is either winning or not. What does it mean? Like, what does it mean to improve? And the answer is that it doesn't make sense. There's no real reasonable notion of strategy improvement in this setting. And in fact, I lied, and this algorithm doesn't synthesize strategies. What it synthesizes are strategy skeletons. So if you imagine a strategy looks something like this, these placeholders correspond to moves of the unsat player, universal quantifiers. The terms correspond to moves of the sat player. And these guards correspond to the conditions under which I should make those moves. A strategy skeleton is the same thing, but with the conditions removed. So it tells me which moves I could make, but it doesn't tell me when to make them. So this is a winning skeleton for a specification of least upper bound, but it's also a winning skeleton for greatest lower bound. So the reason that we do this is because for strategy skeletons, there's a natural notion of improvement. So one strategy skeleton is better than another if more moves are available to it. All right, so this is the thing we're actually synthesizing, and the problem, one of the problems addressed in this paper is how do we go from strategy skeletons into strategies? So how do we do this kind of conditional synthesis? And the approach that we take is to use tree interpolation. It's a variation of Craig interpolation. And I'm going to explain a simplified variant of it now. So imagine that you have a tree in which each leaf is labeled by a formula, and the conjunction of all formulas is inconsistent. That guarantees the existence of a tree interpolant, which consists of a labeling of all the internal nodes of the tree, such that the label of the root is false. The label of a node is always entailed by the conjunction of the labels of its children. And the symbols used by the formula node are the ones that are used by its descendants and non-descendants in this tree. So, for example, N2 is only allowed to talk about a variable x if one of F4 and F5 do and one of F6 and F7 do. So we can pose conditional synthesis as a tree interpolation problem as follows. So we'll begin with our strategy skeleton, and we will replace all of these placeholder values by fresh symbols, and replace those place variables with fresh symbols as appropriate for the moves of the existential player. Then, with each leaf, we'll associate the formula obtained from the matrix of my formula by negating it and applying the substitution that corresponds to the set of terms along this path. All right, what this means is, what this formula represents is the set of all plays in which the existential player, or the SAT player, chose X to be the least upper bound and lost. Right? That's what the negation means. We've lost the game. Similarly, this formula represents the plays of the game where we chose the Y variable or y to be the least upper bound and lost. And since we can't lose in both of these scenarios, the conjunction of these two formulas is inconsistent, and I can compute a tree interpolant. All right, so the conditions of tree interpolation guarantee that the formula that I compute at this branch is going to contain all losing plays along this branch, which is to say that any losing play satisfies this formula. And as a result, if we negate that formula, we get a formula that implies that this path is winning. All right, so we just compute interpolants, negate again, and apply a substitution to replace these underlying variables with regular variables, and voila, we have conditions. That's all there is to it. All right, so this is implemented on top of Z3. We applied it to a bunch of synthesis benchmarks. These top ones are from Cygus. These are from complete functional synthesis. And these are some optimal synthesis problems that are handcrafted. So the challenge here is not to synthesize an implementation of a function, but somehow the best implementation of a function. So this is something that usually involves a quantified specification. And we can see that SimSynth, which is the algorithm that I talked about, performs pretty well. And it's also worth noting that there's a qualitative difference between SimSynth and these other synthesis techniques in that SimSynth, at least in theory, always succeeds. It will always find either a winning strategy for the sat player or the unsat player. So this corresponds to an implementation of the synthesis query or a proof that there is no implementation. So we get negative synthesis results out of this. All right, now reachability games. A reachability game is determined by three formulas that I'll talk about in a bit. It's played on a board that consists of n-dimensional space or d-dimensional space for some parameter d. And the players just alternate taking turns picking positions in this space. The set of initial positions is given by this formula init, and it's chosen by the reachability player. The legal moves of the safe and reach players are determined by these formulas over 2D free variables that tell us when it's okay to move from one position to another. And we require that between every pair of adjacent positions, this formula holds. So the first player to make an illegal move, one that doesn't satisfy their move formula, loses the game. If the game just continues forever with all the players always making legal moves, then we'll just declare that safe is the winner of this game. Okay, so here's an example of a reachability game, which is the game of Cinderella and her wicked stepmother. Cinderella is the safety player. She is, I'll explain that a bit. The idea is that the game board consists of 5 buckets that are arranged in a circle. Each bucket has a capacity, say 3. And at each step of the game, the stepmother will take a liter of water and distribute it however she chooses among all the buckets. And on Cinderella's turn, she picks 2 adjacent buckets and empties them. All right. So Cinderella's goal is to make sure that none of the buckets are ever overflowed, and the stepmother's goal is to overflow one of the buckets. So this is kind of a simplified model of some sort of load balancing protocol. So this can be formulated as a reachability game as follows. You don't have to really look too closely at what these formulas are doing. The idea is that we have 3 or 5 variables, B1 through B5, that represent the contents of each bucket. And maybe an interesting thing to point out is that we encode the losing condition for Cinderella as a precondition on her move. So this overflow formula holds exactly when one of the buckets is overflowed, and this formula just says that Cinderella has no legal moves to make if one of the buckets is already overflowed. So the algorithm proposed in the paper is going to synthesize what's called a safety tree for the safety player. And a safety tree consists both of a winning strategy for Cinderella in this case, and a proof that that strategy is winning. So you can think of this as being like a program plus an inductive invariant. And each of these nodes is labeled by an annotation, which is a set of positions the game could be in. This is like the inductive invariant. We require all the usual inductive invariant conditions to hold in this graph. And each edge is labeled by two things, a guard that tells us when to make the move, and a move, which is a vector that tells us exactly which move to make. All right, so Cinderella can execute this strategy basically just by following the path through this tree. The way that we construct the safety tree is a lot like the way that we verify programs using lazy abstraction with interpolants, if this is a technique that you've seen before. The idea is that we want to unfold the program, prove correctness of some bounded variation of it, and then somehow stitch things together. The difference is that we don't have a program to unfold, we have to synthesize the program that we're unfolding. So to synthesize the program, we can employ satisfiability games. So if we want to synthesize just the next move of Cinderella, that corresponds to a formula form shown here. It just has one quantifier alternation. All right. So I can get a winning strategy for that, and then move on to the next node and say, all right, find me a winning strategy to sort of stay alive for one more round, and again and again. And we see on these 3 rounds, Cinderella has chosen naively to empty the first 2 buckets on each round. So B1 and B2 are the things that are always set to 0. And at this point, we discover that Cinderella has lost, right? So the stepmother can just pour all of her water into bucket 5 and overflow it. So this is a losing strategy. And what we do is we backtrack. So we remove the last move that we made, and we pose a new satisfiability game in which the goal is now to expand to the next 2 moves. So this is how we make progress. So rather than synthesizing the next move, we synthesize the next 2 moves. And this has a bit more complicated quantifier structure, but it's still a satisfiability game. We can use our decision procedure from the early part of the talk. All right. And when we do this, we actually can find a winning strategy, which is conditional. So if bucket B5 has a small enough capacity, we don't need to worry about it. And similarly for B3. And then we kind of make a dumb move again and just empty buckets 1 and 2 for the last move of the game. So again, we'll backtrack and synthesize. And now we end up in a place where we already kind of know a strategy to stay alive going forward. So we're going to use sequence interpolation to kind of force this covering relationship, this backward edge that says, when I get to this node, I just shoot up back to this node. I don't need to worry about expanding anymore. So this corresponds exactly to synthesizing an inductive invariant in lazy abstraction with interpolants. All right, so I can do the same thing on the other side, and I end up with this strategy. Okay, so there's a bunch more experiments in the paper on reachability games, but I'm just going to present the ones for the Cinderella stepmother game. These are a bunch of different variations of Cinderella stepmother with differing capacities of this bucket. And there's no comparison with other tools, and that's not really because there aren't other tools that can synthesize strategies to such games, but they require sort of different inputs. So in particular, they require hints on what the winning strategy ought to be. And this could be a useful thing. It allows us to scale up to larger games. It allows us to express preferences, but also it requires more effort on the part of the user. So the distinction is that this algorithm is completely automatic. It doesn't require any help from the user. All right, but to put some context into how good these results are, I can give you a quote, which is from a paper from POPL 2014, which said that fully automated strategy synthesis within this interval between 1.5 and 3 is unrealistic. And so I guess the interpretation of these results is that they are unrealistically good. Okay, so the contributions of the paper is one, a complete procedure for satisfiability games. This is something that, at least in theory, always succeeds, always produces either a winning strategy for the satisfiability player or for the unsat player, and a sound but necessarily incomplete algorithm for reachability games. This is an undecidable problem. This algorithm may just expand this tree forever. But we do have one positive result, which is that if the reachability player wins in some finite amount of time, we'll eventually find that winning strategy. All right, that's it. Thanks.
Questions. I have one. So you mentioned a very interesting property that because this first procedure is complete, it can give you the result that no program exists that satisfies the specification. What kind of feedback does it give you? So if you're trying to do this like programming from specifications and you're wondering like what's wrong with my spec, why doesn't it exist?
So, I mean, the feedback that it can give you is the strategy. So, in a case that you don't have deeply or heavily alternating quantifiers, this could be as simple as just a model where, like a single input-output example where there's no way. Actually, that's probably not possible in linear arithmetic. I take that back. That can't happen. But in general, it'll just have to be a function that shows that this is an input-output relationship that just can't be captured. So, for example, it might be something like an input for which I'm required to have two distinct outputs, and so there's no function that will compute that.
Very nice presentation, Zach. It sounded, if I understood correctly, as you did backtracking, you were faced with longer, more and more quantifier alternations. Mm-hmm. So in your table of the Cinderella stepmother game, how many quantifier alternations did you encounter, and was it getting more and more as you approached that 1.8 second
yes.
capacity timeout?
I don't have data on exactly how many quantifier alternations it required, but yes. So this gets trickier as you get closer to 2, exactly because the number of, I guess I'll say, stepmother should win the games up to 2. So anything less than capacity 2, stepmother wins, but requires exponentially more rounds in order to prove that. But really, the biggest performance issue in this algorithm is tree interpolation, as it turns out. So I think better tree interpolation is the key to scaling this up more. The actual satisfiability procedure is pretty quick, even with a lot of alternating quantifiers.
And with my tongue firmly inserted in my cheek, are you willing to narrow the bounds for which the challenge should be laid out for the next attempt?
I think anything between 1.9 and 2 would be difficult.